Swayam Prabha. Digital India. Educated India.
So this is a definition of a game for us to begin with. Okay, so a game comprises of the following. You have a finite set here, which is called, denoted by n, which is called the set of players. Now, for each player, for each I in n, you have a set, let us call this Si, which is a set of, now for the moment I am going to call these strategies, and in a few lectures we will produce a more general term for this, but for the moment let us just call these strategies. Okay. So, for each player I, you have a set of strategies. So, if I take say xi in Si, this is a particular strategy here, a particular strategy of player I. Now, if I put together this collection x1 till xn, this here you can think of this as some collection, or you can think of it as a composite vector comprised with these components, however you want to think of it. X1 to xn here is what is called a strategy profile. So, 1, 2, now 3. So, for each I, for each player I, you have a function, let us call this function ui, a function ui that maps this product, right, to R. So, ui maps the product of SIs to R. What is this? This is essentially saying that for each profile of each strategy profile, that means each composite vector x1 till xn, the ui produces for me a real number, and that ui is what is called the player's utility or payoff, various names for this, sometimes called utility, sometimes called payoff. And now ui here is, when I use the word utility or payoff, it connotes that it is something that that the player gains from. So, this is something that the player is looking to maximize. Okay. Alternatively, you can always flip the sign and of this u and turn it into a cost that he is trying to, or a loss that he is trying to minimize. Okay. So is utility or payoff, or let us say cost. So, if it is utility or payoff, the assumption is that he is looking to maximize this, that he is looking for the largest possible value of this, and if it is a cost, then he is looking to minimize this. You put together these three things, then what you get is a game. So, a game basically comprises of a set of players n, a set of strategies for each player, and a collection of utility functions for each player. This here is a game. Okay. And as I said, since we are focusing on non-cooperative games, our underlying here, I need to also, alongside all this, also specify what are the assumptions regarding communication and so on. But so, because we are focusing on non-cooperative games, I am going to assume implicitly that there is basically no communication being allowed between the players. Okay. So, this is a non-cooperative game with these specifications, with this set of players, this set of strategies, and these payoff functions. Is this clear? Now, since some amount of convex optimization and so on will be involved, it's usually convenient to whatever is the function, it's convenient to minimize it rather than maximize. Okay, so coming from usually in a control or machine learning and so on language, we have a cost or a loss that we are trying to minimize, whereas in the social sciences they tend to look at a payoff that a player is looking to maximize. These are just conventions. We will stick to the minimize convention. All right. So now this is the formal definition of a game. So now question is, okay, how are we going to solve this? Okay, so what are we, and to begin with, what are we solving for? Now again, let's be clear. I'm not asking you how to compute. So when I say solve, I don't mean compute something. Okay, compute comes after you tell me what is it that is to be computed, right? So when I am asking for solving, I am asking, okay, what should be the solution? Yeah, so should be, now if I just give you this and I told you the assumption that this is a non-cooperative game, I want something that I should be able to say is a solution of this, right? So if there was only one player involved here, okay, then the problem would become that, well, then the problem would be that there is one player who has a set of strategies and a payoff function which he is trying to maximize. Then it's merely an optimization problem, right? And there is a natural notion of a solution. The natural notion is the optimal value of that particular problem. You look for the global optimizer, or if you are otherwise look for a local optimizer, etc. These are the natural solution concepts from which we derive our solutions. It's a different matter how we go about computing them, what algorithms we have, and so on. But the logic is that, well, it's sort of self-evident that that is what you are looking for. You are looking for a solution of the optimization problem. Now you don't have one optimization problem, but each player has an optimization problem, right? Essentially, there are n optimization problems, and they are all interlinked. The question is, how do you solve this? And again, how do you solve means what should be considered as a solution of this thing, if this particular thing that we've just built. It's a function of the strategies of each player, okay. But what properties should that function satisfy? Without help from someone else, okay. Okay, interesting. Any other? Yeah, so here, one second, just let me answer since this point has been brought up. A game as formulated doesn't necessarily have a winner or a loser. Okay, this is all there is to a game, which has okay, there could, of course, you can take certain special cases in which you can define such a thing as a winner. So, for example, if the payoff reaches a certain value, then you win. Okay, something like that. That could be, but here this is a far more general setting. There is no predefined notion of a winner or anything like that. Yeah, sorry, someone else was saying something. Okay, with what distribution? Okay, but the opponent would be doing the same. So, okay, so here's another important point about games and about how we study games. Okay, now again, once I pose this particular thing to you and I say this is the game and we want to be able to solve it, when we go about coming up with a logic for solving a game like this, we have to first fix a point of view. Okay, point of view meaning that whom are we solving this for and who is solving this game? Is it a particular player in this situation who is solving the game? Are we solving, say, for example, for player 1 or for player 2 or for player n? Are we solving for all of them together? So, this is being solved from whose point of view? So, this is an important thing, right. So, especially particularly when it comes to applying game theory, when you apply game theory, say for example, you want to apply game theory to a security situation where you want to advise say the security of an airport about how it should be deploying its troops to protect the various terminals and so on in the airport. Are you doing this from the point of view of the security company or the security agency, or are you doing this from the point of view of a potential attacker, or are you doing this from a completely different other point of view? So, this is not something that is there in this problem definition. This is again part of the approach that we want to take as far as solving a situation like this is concerned. So, it's a human choice we are making, that we will take the view of not any particular player in the game, but the point of view of an observer of the game. Okay. If you remember, I said initially that we are trying to develop something like a bunch of laws. So, I should be thinking of these players as more like particles that are evolving according to a certain law of motion. The law of motion is that they each looks to maximize his payoff or minimize his cost, whatever. And then there is this interaction between them, that their costs are interdependent. As an observer of this particular system, seeing this particular system play out in the lab, I would want to know, okay, how should I be solving this, or what should be the final notion of a solution of this. So, the point of view we take in game theory is not of any one particular player, but that of an observer of the game. So, we do not do things like put ourselves in the shoes of the players, imagine what the other player would do, and so on. We take the neutral point of view of observing of an observer of the game, in which players are equipped with a certain set of assumptions and a certain set of capabilities. We ask, okay, what should happen? What should they do? Or what must they do? Okay. So, the viewpoint is that, viewpoint taken in game theory is that of an observer of a game. So, you will soon see in a few lectures from now, there could very well be games in which a player is getting bluffed, for instance, okay, by another player, and that if you were in that player's position, you would play differently whereas you would reason about the situation very differently if you were an observer. If you were an observer, you would see that he could get bluffed, but if you were in fact that player, you would avoid getting bluffed. Okay, so the point of view matters. It leads to very different sort of ways of applying game theory and ways of sifting through the logic of game theory. Okay, so we are going to stick to the observer viewpoint. Now, if we are observers of this game, so okay, now again we are back to the same question. We are observers of this game, like the prisoner's dilemma. We are observing that there are these two prisoners equipped with these options and these payoffs. What must they do? And more generally, I mean, now that I have written out a general game, you should tell me what should be the way to reason about this. So, so one of the main landmarks in the theory of games is the methodology or the logic for reasoning about situations like this, situations involving non-cooperative games. And and in fact, even prior to that, the recognition that how you reason depends on whether the game is cooperative or non-cooperative, or whether it is non-cooperative or non-cooperative. Okay. So, all of that observation came from Nash's thesis, and so Nash basically said that if you have a non-cooperative game, then what you should be doing is basically solving it using this particular concept, and that is what I am going to define now. So, the Nash equilibrium is a strategy profile let us call it x1 star to xn star is a Nash equilibrium if the following holds. If ui of x1 star to xn star, so as I said, I have assumed that ui is player is trying to minimize. So, this is okay. So, ui of x1 star to xn star is less than equal to ui of, so I will introduce a notation here. Okay, less than equal to this. I will explain what this means. For all xi in psi and for all I in n. Now, what does this notation here mean? This notation here stands for xi. So, xi comma x minus I star. This notation essentially stands for the following vector. So, x minus I star is the part of the strategy profile in which I have taken all the other players except for player I. So, so I have x1 star, x2 star dot 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 xi minus 1 star, and now in place of player I in place of the starred one I am going to insert this xi here. So, this is xi comma xi plus 1 star dot xn star. So, xi comma x minus I star is essentially this composite vector where I have taken the starred values from the first for all players except for player I, and in place of player I's strategy I have put in this xi that is chosen from here. Okay. So, that's the notation for xi comma, that is what this notation means, xi comma x minus I star. It is a notation specialized for game theory because this kind of a thing comes up all the time here. Okay. So, now let us see what Nash is basically saying. So, what Nash is saying is that we should be looking at a point x1 star to xn star is called a Nash equilibrium if the following holds. So, what do we have on the left hand side? On the left hand side you have the cost of player I when this strategy profile is played. When the players play x1 star to xn star, the n players, all of them play the starred value. What I have on the right is the strategy profile is the cost of player I when the strategy profile changes to xi comma x minus I star. That means all the other players stick to the starred value, the starred part of they continue to play the strategy, the starred strategy, but player I switches to xi. Okay. So, what this is saying is that player I is here, what this inequality is saying is that a player I is better off playing the starred value than he is by switching to some other xi, provided the others stick to their starred values. Okay. And this holds for every xi, and moreover this holds not just for this particular player I that you have chosen, this is symmetric, it holds for all players. So, every player I prefers to stick to his starred value, starred strategy, provided the others do not switch from, do not deviate from their own starred values. So, no player has an incentive to deviate from his strategy from the profile, provided no one else deviates from their own strategy in the profile. Okay. So, this is called the Nash equilibrium. Now, why is this such a big deal? Why is this I said this is a landmark in the theory of games, and why is that the case? The reason is basically this. Essentially, what Nash gave us is essentially a watertight way of now reasoning about games. What is this situation? What is this inequality really saying? What this inequality is saying is that if I want a point x1 to if I want a profile x1 star to xn star to be considered a solution, then this must hold. What must hold? Well, no player should have an incentive to deviate unilaterally from that profile. So, assuming the others stick to their strategies in the profile, I would not want to deviate from my own strategy from the profile. Now, why is this correct or reasonable? Why is this logical for a non-cooperative game? The reason it's logical is because, see, once a game is non-cooperative, only unilateral deviations are feasible. There is no way for a pair of players or a group of players to form a unit and then deviate together. Like it happened with the Shiv Sena, for example. You cannot have that kind of a possibility where a bunch of players come together and deviate together. What is happening here? So, in a non-cooperative setting, when there is no communication is allowed between players, only unilateral deviations are feasible. If only unilateral deviations are feasible, well, then what it means is, if any point has to be considered a final solution, then it has to be stable against such deviations. Because if not, then the adjustments process is still going on. Whatever you are at is not a solution anymore, is not an outcome anymore. So, this is essentially a necessary condition for any profile to be considered an outcome. If it has to be an outcome, it has to be a Nash equilibrium, right? Because otherwise, that if it is not a Nash equilibrium, then it means that there is at least one player who, under the communication constraints, can deviate from it. And if that is the case, then whatever you were considering earlier from that point is not an outcome anymore, right? Something else could potentially become an outcome. The adjustment process continues, the reasoning process continues, and maybe there is some other outcome. So, what this basically does is essentially it gives us clarity on how we should be thinking about non-cooperative situations. Non-cooperative situations, you ought to think of them as something where players, if they could unilaterally deviate, they would. So, if you want a final solution, or if you want anything to be considered as an outcome, then it has to be of the kind where unilateral deviations are not profitable for the player anymore. All right. So, this is the Nash equilibrium of a game. Okay, and so this is the solution. This is basically the most widely applied solution concept in any non-cooperative situation. You will as you go forward, you will see how the kind of amazing properties it has and so on, and how much it is able to explain about strategic interactions and so on. But for the moment, let us just go back to the prisoner's dilemma and let's see what is the Nash equilibrium for the prisoner's dilemma. Yeah. Yeah, because in a non-cooperative game, only unilateral deviations are feasible. If you take the same situation in which you have a cooperative game in which a bunch of players could communicate and say, well, as a group we want to move from one sub profile to another sub profile, right? That would be a different game, and that would be a different type of situation, and it would lead to a different type of concept. In fact, the coalition formation games, which is a kind of cooperative game, there you solve the game using exactly these lines of reasoning. Okay, about what kind of coalitions are stable. Well, the coalitions that are stable are the ones where in which no subset of players can actually deviate from. But here, because this is a non-cooperative setting, only individual player can deviate. Yeah. So, what is the Nash equilibrium of the prisoner's dilemma? 2-2, right? Testify is the Nash equilibrium of the prisoner's dilemma, and the reason for that is that if you see how are we arguing here? We need to argue that assuming the other player plays his component from this profile, I would not want to deviate from my component, right. So, assuming the other player plays testify, I would not want to, assuming B plays testify, A would not want to switch to silent, and likewise if assuming A plays testify, B would not want to switch to silent. Now, this game is symmetric, and that is why this computation is this is very easy, okay, and but of course, in general the number of strategies that players would have could be different for each player and so on. All right. So, let us take another example. So, here is another example. This is also symmetric. This is an example where there are two hunters, okay, hunter 1 and let us say hunter 2, and they are both poised to hunt down a deer. Okay. They are both poised to hunt down a deer. I mean, let us assume that they are sort of at two different there's a deer in some central location, and they are both viewing that deer from two sides. They cannot communicate with each other. I mean, of course, there could be visual cues and this and that, but let's assume that is not possible. They cannot communicate with each other. They are both seeing this, poised to hunt a deer, ready to hunt a deer. But then suddenly there is this option that a rabbit runs by. Okay, and then there is the possibility to also hunt a rabbit. So, and what is the dilemma? The dilemma is the following, that a deer is much bigger and takes much more effort to hunt. Okay, so if both go for the deer, they will be able to hunt down the deer, and they would each get, let us say, a payoff of 2. But if only one of them goes for the deer and the other goes for the rabbit, the fellow who is going for the deer will not be able to hunt the deer alone. Okay, so the one who is going for the rabbit gets the rabbit, but the one who is going for the deer doesn't get the deer. Okay, so, and if both go for a rabbit, the rabbit is much smaller than the deer, and so what they will each get is whatever, half. Okay, so now again, what's the reasoning here? So, one thing you will notice right away is that this is not a situation like the prisoner's dilemma, where there is one strategy that is uniformly better than the other one. It is not true that regardless of what the other guy does, it is better for me to go for the deer, right. In fact, this is more akin to the coordination problems that I was just talking about. We are both better off if we coordinate, but coordinating on a better thing is better for both. What's the logic here? Again, we do not want to get into the trap of trying to predict what players will do, because we again do not know what they will each do, because that gets into a whole bunch of other issues like how hungry each hunter is, how selfish they are, and so on and so forth, the amount of trust they have in the other individual and so on. That is not our mandate, that is not our competence. What we want to do is come up with a bunch of reasoning rules by which we can say what is the logical outcome. Not necessarily, and the reason is because whatever the other player does arises, your distribution of what the other player does, for example, is part of the strategic posture of the other player. So, it is not, the point is, you may see, this is a temptation in games all the time, right, that instead of trying to say, well, I can think from the point of view of a player, and I say, okay, maybe the other hunter 30% of the time goes for the deer and 70% of the time goes for the rabbit, and then based on that I will try to decide what I should do. But remember that 30 and 70 is not a phenomenon, is not just some fact of nature, it is part of his decision. How often he should be going for the rabbit versus deer is part of his strategy. All you have done by just bringing in these probabilities is just lifted the same problem to the space of probabilities. Now each player has to decide not whether to go for rabbit or to go for deer, but rather how often he goes for rabbit or with what probability he goes for rabbit versus what he goes for, whether as opposed to deer. So, this trying to model the other player using some probabilistic model basically just gets you to one the same reasoning sort of conundrums that you had even in the strategy space. Okay, you just need, so you have the same issues just in a different space. Look at the classic case of the Normandy landings in Normandy, right? So you could during the World War there was this this very epoch-making event where the Allied forces landed in France to liberate France and from Germany, which was occupied by Germany at that time. They picked two possible locations for landing on the northern coast of France. One was called, the name is Normandy, the other is Calais. The Germans also knew that these were the two potential landing locations. All right. What they did not know was where they would actually land. Okay. You could say, well, I do not know where they would land, but I think I have a certain model based on which I think that is where they were likely to come. But where they are likely to come depends, and how well you will succeed depends also on what you are planning to do. Just like you are making a model about, just like the Germans were making a model about where the Allies would land, Allies would be making a model about where the Germans would keep their defense. You are effectively just elevated the problem to deciding how should we distribute our troops, rather than trying to decide where we should be keeping our troops. So that is all there is. This thing only changes this particular flavor. Now, to be fair, there is another type of a class of games called repeated games, where things tend to get a little more intricate, where we are playing this game not just once but multiple times. Okay, but with the knowledge that this is being played multiple times, and then you can try to sort of bake in some of the issues, some of the things that you have in mind. But again, this is for the first lecture. It's too complicated to get into that. Okay, yeah. So what's the logic? Then that's a very different game. That's a very different game, because that's part of the assumptions then, that you know certain things about the other player. Yeah, so the assumption here, the way I have stated this game, in this here, is that there is no such information. All you know is this. So in fact, an important thing is, okay, which some of you should have asked me before, what do players actually know? Right? So these players are choosing their actions without communicating with each other. Right? But what do they know? Well, the only thing that they know is this table. Okay, so in the case of the prisoner's dilemma, they know this table, that this is what has been offered. They are choosing their actions without the knowledge of what the other player is doing. Okay, so as good as simultaneously. So they do not know what the other player is doing. In the World War example, essentially we do not know where the Allies are going to land. Okay. If that is known, then that's a very different game. Or if that is known even with some noise, that's a very different game. Or if I know even that there is a certain probability with which they are likely to land, that's also a very different game. That's not the game that's being discussed. No, it's it's not. See, so information changes the character of a game. So if I know that, say for example, there is a point of no return after which the Allies are going to land in a particular location, right? then that's a very different game. How I strategize will change very differently. So let's come back to this then. Players know this table. They know that each player wants to get the maximum payoff. They also know that this is how the payoffs of deer and rabbit and so on are. You know, this is what the values are. Now, what's the logic for this? So you cannot, obviously there is no strategy here which dominates the other strategy, which means that regardless of what the other guy is doing, this is always better. That kind of strategy doesn't exist. But we can try to reason about this through the Nash equilibrium. So if you see, essentially what Nash is saying is, whatever is the final, you know, each player would think, okay, decide, okay, should I go for deer, should I go for rabbit, etc., etc. Whatever is the final, if at all there is a resolution of this, as if we were observing these two hunters, what they would do is, what they ought to do is that either both go for deer or both go for rabbit. Okay. Now, why is that the case? So, if you look at let's say deer. Now, deer is a Nash equilibrium here, because assuming the other guy is going for deer, I would want to continue to play deer. Okay. Likewise, rabbit is also a Nash equilibrium, because if the other guy is going for the rabbit, it doesn't make sense for me to try and get the deer, because I won't be able to get the deer alone. Okay, so it's better for me to stick to rabbit. And deer rabbit is not a Nash equilibrium, or rabbit deer is not a Nash equilibrium. So there are two Nash equilibria in this game. Okay, deer is a Nash equilibrium, rabbit is also a Nash equilibrium. Let's conclude today's lecture with just this global picture. So essentially, if you want to position a non-cooperative game theory, then you could position it in the following way. You can think of the single player setting, and this is the multiple players setting. Single player and multiple player. Now, the first setting and the kind of games that we have seen so far is what are called static games. Static games is where no player has any information about anything else apart from what he starts off with in the game. So he does not know what the others have done, does not know what else has happened, and so on. If any other evolution has happened, and so on, he does not have any such information. Those are what are called static games. So player just plays once and with the same with a sort of a null information, except with only the information about the payoffs of the players. Those are called static games. Now, in the static setting, if it's just one player, it just reduces to optimization. And if it's multiple players, then it leads to static game theory. On the other hand, if the setting is dynamic, which means that there is either a time evolution or there is an aspect of information and so on, then in that case the one player case is what we know as optimal control. Optimal control with under various names, stochastic optimal control or whatever, and in the case of multiple players, it leads to what is called dynamic game theory. So my effort is going to be to quickly run through this so that you are familiarized with the basics, and then we will spend about 70% of the course on dynamic games.